Well, hello, welcome again to Math 315, Analysis and Topology, and this is the second video of Chapter 2. And so we've been looking at the epsilon m definition for limits, and as I pointed out last time, the concept of this, just to quickly remind you again, the concept of this is our definition of this limit. We say that this sequence AN tends to L. If given epsilon bigger than naught, we can find an M, so that if I go past that point, then the distance between the sequence and its limit is less than the epsilon, the width of the band. And so geometrically, we were taking our limit, we're putting a little epsilon band each side, and then eventually the sequence moves inside the band and stays there forever. And that's the definition we're going to apply, and I did a couple of examples of that. I'm just going to do another example here, follows on from something we did a bit earlier. We're going to find this limit, the limit as n goes to infinity of root n plus 1 minus root n, which we've done something like this before, but this time we're going to give a proof of that our result is correct using our epsilons and m's. So here is the solution to this, and here's the question. We're taking this limit. Now we have done this before, but I'll just go through it again because we can use some of the calculations a bit later. So remember, the idea was that we've got these square roots on the top, and we wanted to get rid of the square roots, at least from the numerator, and we did that by using this trick here. We multiply top and bottom by conjugates. And what that does, of course, is by using the difference of two squares, it's going to move the square roots from the top down into the bottom, and then hopefully something nice happens. So I take this expression, I change the sign in the middle, and I multiply top and bottom by this new expression. So I'm going to get this squared minus this squared, and that's going to give me n plus 1, that's the square of this one, minus I square root n, I get n. And in the denominator, I've just got root n plus 1 plus root n. Now, happily, the n's cancel out here, and I just get a 1. We saw this happening in an earlier example. And I just get 1 on n plus 1, root n plus 1 plus the square root of n. And now I can just use my common sense and say, look, as n gets very big, then this is getting very big, this is getting very big. 1 over big is small, so in the limit, this is going to 0. That's just doing it heuristically. Now we're going to give an epsilon m proof that this limit is in fact 0. So the usual mantra, we begin by, given epsilon bigger than naught, put m equal to, I'm not sure yet, I'll tell you in a moment. And then if n is bigger than capital M, if I go past that m point, then I have to squeeze the sequence minus its limit, and I've got to squeeze that less than epsilon. Now, we saw above that we could take this expression in here and we could rewrite it in this form after we'd rationalized the numerator. So I can take this and I can rewrite this as 1 on root n plus 1 plus root n. It's just the same calculations we did above. Now, I look at this here and I try and see where the rubbish is. What would I like to throw away? Well, I'd like to throw away this plus 1 because then I can combine these together. And so again, I use inequalities. Inequalities enable you to throw out the rubbish. So I throw out the rubbish, which is this plus 1 here, and I toss that away and I replace that with just 1 on square root of n. Now, root n plus root n is 2 root n. So we've now squeezed this less than something simple. And now I always go back, once I've got it down to something simple, I always go back and use the fact that n is bigger than m. So this is less than 1 on 2 square root m. So I get everything now in terms of m. I haven't told you what m is yet. And now I simply make this equal to epsilon. And all I've got to do now is I've just got to fill in the gap up here and tell you what that is going to be. So as a little side calculation, I'll turn both sides upside down. Turn both sides upside down. And I'm going to square both sides. So I'll get 4m is equal to 1 on epsilon squared. And finally I can just divide by 4. So I get 1 on 4 epsilon squared. So all I've done is I've just solved this equation here for m, and it turns out to be 1 on 4 epsilon squared. And now I go back and I fill in the gap before anyone sees. I fill in what the m had to be. And again, just to check the logic, I tell you how wide the epsilon band is. It's epsilon. I have to go out as far as 1 over 4 times epsilon squared. So if epsilon, for example, was 0.1, then I'd have to go out to, so 0.1 squared is 0.01, and that would be then 100 on 4, so I'd have to go out 25 across the x-axis, across the n-axis, 25 terms in order for this to work in that case. So I put m equal to this, then if I go past that point, here's the calculations show us that the difference between the sequence and its limit, I just trace it through, is less than epsilon, the width of the band. So I've satisfied the definition. So that was just a slightly more interesting example, and there's another one of these in the tutorial problems to have a look at. Now I wanted to show you one harder example, and this is much harder in fact, and I don't expect you to be able to reproduce this, but you might like to try and follow through all the steps. This is a more difficult limit to prove, and we're going to use the definition. We're going to prove that the limit of n to the 1 on n is 1. Now again, you can't just whack n as infinity. I'm not saying infinity to the 1 over infinity. That doesn't make any sense, but what I'm saying is that n gets very big. When you take the nth root of n, you get closer and closer to 1. You might like to play with this on your calculator. For example, if I took the 100th root of 100, then I'll get a number that's close to 1. Won't be equal to 1, but it'll be close to it. If you take the 1000th root of 1000 on your calculator, again you'll see you're getting a number close to 1. And that's what we're going to prove. Now for this I'm going to use the binomial theorem, which I hope you've met before. It's in the high school syllabus and you would have done it various places, and it's very important, and we will use the binomial theorem again from time to time. It's often a good source of good mathematics hiding in the binomial theorem. So I'm going to expand 1 plus x to the n, and so from the binomial theorem we get 1 to the n is 1, and then I get the binomial coefficient n choose 1 times x to the 1, then I get n choose 2 x to the 2, and I should have in here plus dot dot dot. So there are lots more terms going on here, and n choose 1 then is just n. You do some simple calculations here. So n choose 1, remember, is n factorial on 1 factorial by n minus 1 factorial, and if you simplify that, that just gives you n. Similarly, n choose 2, well, n choose 2 is going to be, I'll just pop it up here, n choose 2 is n factorial 2 factorial n minus 2 factorial, and you can do a bit of cancellation here. This is n times n minus 1 times n minus 2 factorial over 2 factorial is 2n minus 2 factorial. These cancel out, and you just get n minus 1 over 2, and that'll be multiplied by x squared, plus dot dot dot. Now I'm going to toss away the dot dot dots. I'm going to say, well, all these terms are positive, x is positive and n's bigger or equal to 1, so I can toss away all of the terms in here and say, look, this is just bigger than n plus nx plus n into n minus 1 on 2x squared. That is, I can toss away all this and just keep the first few terms. And indeed, I'm going to toss away a bit more. I'm going to toss away the nx as well. So, hence, this 1 plus x to the n is bigger than 1 plus, I'm going to toss this term away as well and just keep the first term and that one. Inequalities, the art of throwing out the things you don't want. And like in this problem, I don't particularly want the nx term, as you will see. Well, okay, now I'm going to choose, this was true for any x I like, positive, and I'm going to choose root 2 on root n. Why? Because, well, it turns out it works nicely. So I'm going to choose that there, root 2 on root n. So this is just a trick. So we plug this in, I get 1 plus root 2 on root n to the n from here, and this is bigger than n minus 2 on 2 times x squared. And so when I square this, I get 2 over n. And now you see why I choose this, because the 2's cancel, the n's cancel, and I just get n minus 1 here, and n minus 1 plus the 1 here at the beginning all collapses down to n. So just check the algebra here. The n's go, the 2's go. I get 1 plus n minus 1 is just n. And that's why we made this choice. Okay, so we can now, from here, we can take the nth root of both sides. So the nth root of, so this is going to be n to the 1 on n now, and that's less than this thing, 1 plus root 2 on root n. So I've just taken the nth root of both sides and written the inequality around the other way, and I get that. Finally, now we come to our epsilon n definition. So I claim that the limit of this thing is 1. So here's our mantra: given epsilon bigger than naught, then for n bigger than m, I haven't told you what m is yet, so I'll do that in a moment. I want the difference between the sequence and its proposed limit, which is 1. I want to squeeze this less than epsilon. Well, what we've done here is we've shown this is less than 2 on root m. Now root 2 is less than 2, and n is bigger than m, so this is less than root m. And I'm simply going to take this to be my epsilon. Take this to be my epsilon, and I can now solve this here by taking, I'll just turn both sides upside down and square it and rearrange, and this will be certainly less than epsilon or equal to epsilon if m is, well, I should leave it as it was. So this will be less than epsilon. Normally we put it equal to, but I'll just put it less than here, doesn't matter. So it's less than epsilon if we take m to be bigger than 4 on epsilon squared. So I've just rearranged this and made m the subject. So that's a more difficult example where we needed a more complicated inequality, and I wouldn't expect you to be able to reproduce that, but we will see this idea of using the binomial theorem in various situations, and any question like this you'd have to be led through very carefully. Now there are further examples of this, as I mentioned, in the tutorial problems. Well as convergent sequences, we also have divergent sequences, ones that go off to infinity, and there is also a formal definition for sequences which diverge to infinity. And I'll just do a little bit on this. We're not going to worry too much about these divergent sequences. We're more interested in proving things converge, but a sequence A sub n diverges to infinity if, well, if it's getting bigger and bigger, it simply says that if I put a brick wall anywhere, then eventually the sequence gets beyond the brick wall. That's the basic idea of what we mean by diverge to infinity. The terms just keep getting bigger and bigger and bigger. So if I try and stop them somewhere, well, it doesn't work. You can eventually get past that barrier. So in other words, for any given h bigger than 0, so there's my h, eventually, that is, there is an m, so that if I go past that point, then the sequence is bigger than h. No matter where I try and put the brick wall, eventually the sequence goes past that brick wall. So this simply says that the terms of the sequence are getting as large as we like the further out we go. The further out we go. Well, just a simple little example here. We've got an as e to the n, so this is e squared, e cubed, e to the fourth. Clearly this is going off to infinity, and this is a divergent sequence, but I want to show that using our definition above here. So here's a little solution proof of this result here. So here's my an, it's just e to the n, e is our old friend, 2.71828 approximately. Now what do we want? We want to know how far out do I have to go. So I give you the barrier, there's my h. I want to know how far out do I have to go so that e to the n is bigger than h. So I'm going to look at that inequality here. And I can solve this now for n by simply taking logarithms to the base e. Now by the way, when I write log log or ln or log sub e, all of these mean the same thing. We use various notations for the natural logarithm. So if I have log, then it's always understood to be to the base e, and sometimes I'll write ln. Anyway, so I'm going to take logs of both sides, and the log of e to the n to the base e is just n, and the log of h is the log of h. And that simply says that if I go past this point, if I take m bigger than the log of h, then for all n bigger than this capital M, I could even take m equal to the log of h, take any number n bigger than m, then the sequence is bigger than h, because that's how we constructed this number in the first place. So that's just a simple example of showing from the definition this particular sequence diverges to infinity. Now we note that a sequence which doesn't converge may not necessarily diverge to infinity. So a sequence could be what we call boundedly divergent. That is, it neither converges to a finite limit, nor does it diverge to infinity. And a couple of examples of these are -1 to the n and sine n. So again, let me just come back and look at these two. -1 to the n, as n takes on positive integer values, well, if n is 1, you get -1, -1 squared is 1, -1 cubed is -1, and so on. So it's not converging, it's just bouncing back and forward between -1 and 1. And another example is sine of n. So sine of 1, sine of 2, sine of 3, and so on. And we can sort of graph that if we just draw our old friend the sine graph, and we simply take the points on here corresponding to the value to integer values. So we take the sine of 1, sine of 2, and so on, sine of 3, sine of 4, sine of 5. We're just going to get these crosses here. And again, this sequence is not approaching anything, it's just wandering up and down along the sine curve. So this sequence is not going to converge. On the other hand, neither of these sequences zip off to infinity. So these are examples of what we call boundedly divergent series. So I'm going to prove now a theorem that you probably think was fairly obvious. It's not easy to prove. In fact, I'll go through the proof of this, and the proofs, again, I don't expect you to be able to reproduce the proof, but you should try and follow through the logic of it. It says if I've got a sequence A sub, if this converges, then its limit is unique. If I've got a sequence, I suppose technically I should put some curly brackets around that, but I've got a sequence A sub n. If it converges, then its limit is unique. You can't get two different limits from the same convergent sequence. And it's a fairly obvious thing. You would hope to be true, that when you take your limit you only get one answer, and in fact we're going to prove here that you do, but again we're going to do this using the definition. So suppose we have a sequence a sub n which converges to two possibly different limits, x and y, and we're going to prove that x and y in fact had to be equal to each other. So with a sequence, we're going to suppose that it converges to x and converges to y, and we're going to show that x and y are in fact the same. So we do this by going back to the definition. So given epsilon bigger than naught, we can find real numbers m1 and m2 so that this is true. The sequence an converges to x, so that means given epsilon bigger than naught, if I go, there is a number m1, so that if I go past there, then the difference between an minus its limit is less than epsilon. Well, I'm going to choose epsilon on 2 again, just to make the last line neater. Could have just put epsilon here, but I'll put epsilon on 2, because certainly if it's less than epsilon on 2, it's going to be less than epsilon as well. So I can make that epsilon on 2. And then similarly, this sequence an goes to x, so that means eventually there is some m2. Once I go past there, the difference between an and y is less than epsilon on 2. So I'm just making the width of the band half of what it was if I just had epsilon. Okay, so we keep those in mind, and what I'm going to do is, again, I mention here that I choose epsilon on 2 rather than epsilon, simply to give an elegant last line. It really doesn't make any difference. I'm just making the band a bit thinner. Now I'm going to look at the difference between x and y, and the name of the game is to show that this is as small as I like, and that means x and y are equal. So what I do is I'm going to subtract and add. I've got to get the sequence into the story somewhere here, so I'm going to subtract the ANs and add in the ANs, and I'll just bracket those together. So I subtract and add the same quantity, bracket these together. Now I can use the triangle inequality, which we've mentioned before. We're going to be using constantly in this course. So this is less or equal to the absolute value of this term. Well, you'll see I've just multiplied by minus 1. It doesn't change. The absolute value of that's the same as the absolute value of that, because these differ by a minus sign, and the absolute value of minus 1 is 1. And then plus the absolute value of an minus y. So just note that step. I've used the triangle inequality, and I've just multiplied this by minus 1, which doesn't affect anything because I've got absolute values. And this one was less than epsilon on 2, provided I went far enough. And this one was less than epsilon on 2, provided I went far enough. And so I'm going to take n to be bigger than the maximum of these two. So therefore, both of these inequalities are correct. So this is less than epsilon on 2. That's less than epsilon on 2, because I've gone past these, the maximum of these two. And this simplifies down to epsilon. So if we now look what we've written, we've got x given any number, no matter how small, the difference between this x and y is less than this epsilon. And since epsilon is arbitrarily small, any two numbers that can be made arbitrarily close together, they have to be equal. And that proves that the limit of the sequence is unique. So I'm going to now introduce an important concept, the idea of bounded sequences. So we say that a sequence AN is bounded simply means there is a brick wall that it can't get past. We saw that for divergent sequences there was no such brick wall. As soon as you put a brick wall, for a divergent sequence you can get past that brick wall. For a bounded sequence there is a brick wall somewhere here, and the sequence, it can wobble around a bit, can do all sorts of crazy things here, but the sequence can't get past this height. That is, the absolute value of an is less or equal to k for all n, or perhaps for all sufficiently large n. Sometimes the first couple of terms might start up above it, but eventually they're all going to be less than it. Now, an example of a bounded sequence is sine n plus 3 is a bounded sequence, because the biggest sine can be is 1. So if I take the absolute value of sine n plus 3, the biggest that can be is 4. So this is less or equal to 4 for all n. So this is a bounded sequence. Now, by the way, this doesn't converge. We saw before that sine n just wobbles along the sine curve, and adding 3 not going to make much difference. So this is bounded, but it doesn't converge. So note here that bounded sequences are not necessarily convergent. Here we've got an example of a bounded sequence that is not convergent. So the above example shows this. However, the converse is true. That is, here's our little lemma here, any convergent sequence is bounded. So if you've got a sequence that you know converges, then there's a brick wall somewhere and the sequence can't get past that brick wall. Now again, the proof of this is fairly tricky. I don't expect you to be able to reproduce the proof, but you should try and at least get some gist as to how it works. So we suppose our sequence converges, so the limit as n goes to infinity of an is equal to a. Now that means for any epsilon bigger than 0, well, I choose epsilon to be 1. I'm going to take epsilon to be 1 in this problem. We're allowed to take epsilon to be anything, and here I choose it to be 1. And because this limit exists, there is a positive integer m, so that if I go past that point, then the difference between the sequence and its limit is less than the width of the band, which in this case I've chosen to be 1. Now again, we're going to use the triangle inequality, and we're going to look at how big the nth term can be. So the nth term then, and again I'm going to use this old trick, I'm going to subtract and add the same number. I've got to get the limit a into the problem, so I'm going to subtract it and add it. And I'm going to put some brackets around the first two terms, and then I'm going to use the triangle inequality to say that's less than the absolute value of an minus a plus a. Now up here we had that the absolute value of an minus a is less than the width of the band, which was epsilon, so this is less than 1 plus the, again using this triangle inequality, it's 1 plus the absolute value of a. This is a fixed constant. So that tells me that eventually, once I get past m, eventually every term is bounded above by this constant 1 plus absolute value of k. There's my k here. Now, I've got to be careful because that only happens after I've gone through past the mth term. So I've got to worry about what about all the terms before. What about the first term, the second term, and so on up to the nth term? Well, to take care of that, I'm going to put my constant k now to be that whichever's bigger, the maximum of the first m terms and this quantity, which we know am is less than this quantity, provided we go past the mth term. So I take k to be the maximum of all of these numbers, and then we therefore have k is bigger or equal to the first m terms, because we made it that way, and also any term after the mth term, k is going to be at least as big as that, and that means the a sub m is less than this k. So hence we have the absolute value of an is less or equal to k for every n. And so the sequence is bounded. Now, in practice, we'd like to not have to go through all these epsilon m proofs and things. We'd like to be able to use our intuition to evaluate limits, as we've done in the past. And we're going to see that we have a nice theorem coming up in the next recording called the algebra of limits that will enable us to do just that.